Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The first section in astronomy is fundamentally based on ALMA. And the second section on visualizations will discuss a worldwide telescope. Now, in the case of ALMA, I cannot think of a better combination of speakers than the ones we have today. On the one hand, we have Doug Roberts. He's a professor of physics and astronomy at Northwestern. He's a scientist interested, I gather, in formation of stars in extreme environments. So he will give you the perspective on ALMA from the point of view of the user, the astronomer that comes to this national facility and uses it. On the other hand, Juan Cortés, whom I've known since his times in graduate school, is a joint ALMA office operations astronomer. He has a PhD in astronomy, and he fits very well the description that Tony Hay gave this morning of what you call a data scientist. Of course, he's an astronomer, he has his own projects, but he's responsible, among others, to verify that the data that ALMA is providing the external observers is being verified. It has the Nile-Obstadt print on it, and it can be used and has been properly calibrated. So he is a generator of data for the astronomical community from ALMA. And he will describe ALMA from the internal point of view, the point of view of those who are, as I said, providing the data. So we will divide this in 3 talks. The first talk will be given by Doug, followed by Juan, for ALMA, both of them. And then, again, Doug will discuss the Worldwide Telescope. 25 minutes plus 5 for questions.
Okay. So thank you for having me here. As Eduardo mentioned, my scientific interest is star formation in extreme environments, and there's no more extreme environment than the gravitational environment very close to a black hole. And I'll get to that in a second. I do want to make one point about why ALMA is so special from my perspective as an external scientist. Tony mentioned a golden age for computer science is upon us, and I think we're also at a similar phase for astronomy. And as an astronomer, one of the things that really always kind of surprises me, even though I'm embedded in astronomy and I have been my whole life, is how quickly the human race, once we realize that the electromagnetic spectrum that we see with our eyes, in this spectrum, the color of the rainbow, visible light, is only a tiny fraction of a very large, expansive electromagnetic spectrum that reaches from long wavelength radio waves in one hand all the way to gamma rays in the other. Once we detected the first extraterrestrial radio signature, which was in 1930, it was actually from the black hole that I'll be talking about. We very quickly filled in all these gaps. We built kind of survey quick instruments to find out what was there, and then afterwards we developed very sophisticated, powerful instruments that are almost at this point limited by the physics of how you build receivers and how you and some of the economics of how do you support spacecraft and so forth. So in the far wavelengths, by the way, the one thing about this plot to note is the bottom, this bottom graph here shows the transparency of the atmosphere. So all the things on the energetic side of visible light require us to get above the atmosphere. So that required, in the early days, balloons, and now the premier telescopes require spacecraft. And of course, that was inaccessible to us until we knew how to use rockets to get us above the atmosphere. And then on the redward side of the optical spectrum, premier telescopes, some of them are required to be above the atmosphere, like Spitzer, which is a telescope that looks in the infrared. Our atmosphere actually absorbs much in the infrared, so we have to get above the atmosphere for that. However, the part of the spectrum that's most transparent actually is actually in the radio wavelengths. And so the ground is an effective place to build radio telescopes. However, short wavelength radio waves, which is what ALMA observes, have this issue of where the atmosphere isn't, where you're looking at the molecular lines from astrophysical objects, and you don't want to see molecular lines from our own atmosphere. So it's important to get them to a high location, to not have very much water content above us. And Chile is an excellent place for that. And I think Eduardo tomorrow will talk about Chilean astronomy and some of the capabilities and kind of directions it's going. But it's a fantastic place for that. And so ALMA really provides that opportunity. The things that ALMA, as a scientist, provides to me are kind of, I think of three different kind of capabilities. One is resolving power. So every telescope has a certain limited resolution. If I were to look at a point at a great distance, it would appear to be a certain size in my image based upon many parameters. Ultimately, it's the size of the telescope. So at some level, if you're limited by, it's called diffraction limited, where you're limited only by the size of the telescope. As you make them bigger and bigger, you're able to see smaller and smaller details. And ALMA is for its wavelength range of being short wavelengths, provides a very high resolution. The other is coverage, or it's called visibility plane or aperture synthesis coverage, which reflects image fidelity. So without good coverage, so all these telescopes, the very large array and the radio wavelengths, which are bigger telescopes but less accurate, and ALMA in their millimeter wavelengths and submillimeter, which are smaller telescopes but very finely precise. You lay them out in some pattern in some area over a large, ideally flat plane, but there aren't flat planes that are at high altitudes, so it's usually somewhat jumbled up. And the number of those telescopes you have simultaneously looking at a source, essentially, the more telescopes you have, the less artifacts you have from missing coverage. So ALMA is spectacular for that. And the third one is essentially the wavelength coverage. In the case of a radio telescope, an optical telescope, a lens or a mirror forms the image, and it focuses that image on a detector like a CCD, like your digital camera and the Hubble Space Telescope work the same way. The way a radio telescope works is you actually capture the light field and you reconstruct the image using a device called a correlator, which makes that image. And in previous generations of millimeter wave telescopes, I had to make I could only see a small fraction of this plot. So this plot here, I could only see like one of those lines. I may not be able to even detect the whole thing. And so I was always wondering what's at the edge of the line, and I could only see one at a time. It became very difficult to interpret. And with ALMA, it has a very sophisticated correlator where I can see many lines simultaneously, and that provides a lot of power to be able to observe many different molecules at the same time. So now, so I've given you a little background on the instrument, but now the science that's driving me to use the instrument is essentially looking at our galaxy, the center of our galaxy, as a place to understand how stars are formed in the galactic center. And so this just gives you an example of three different galaxies. The one on the left is an artist's conception of our galaxy looks face on. We're in the middle of a flat pancake of a very dense, thin disk. And so when we look through it, we're in the forest looking at the trees. We can't really see it like this, but this is what we think it is, with a bar in the center and then a two-arm spiral coming out. And at the center of our galaxy, and we'll show this in a second, is Sagittarius A star, which is a radio point source at the position of this black hole that we're actually very certain is about 4 million times the mass of our sun. Andromeda, which is our next nearest large galactic neighbor, which is very similar to the Milky Way in most respects, also has a black hole of a few million solar masses. But both these galaxies harbor black holes that are quite small in comparison to the largest of them. And the largest that we know is M87, which is a very distant galaxy, which has a massive black hole, which is 1,000 times larger than our black hole. So it's billions of solar masses, not millions of solar masses. So this is a general, and so it's very perplexing for scientists to say, why would some galaxies harbor massive black holes and other galaxies harbor small black holes? And we're trying to understand that evolution. The other kind of questions driving all this is, what's the recipe for making a galaxy? So we know the galaxies have gas and dust. We know they have stars. We know they have this material called dark matter, which comes in two forms. One is things like planets and asteroids and small black holes that don't emit light. and the other part is this more exotic material, which is in the halos of galaxies and actually surrounds all normal matter. This is something that we're looking for in laboratories. But the matter that we see is only a fraction of the universe, and most of it isn't dark matter actually. And then we also know that supermassive black holes are a major constituent of the galaxies themselves, but we don't know how they all move together. Now, at the center of our galaxy, when I mentioned that we have a very accurate determination of its mass, it becomes because of the black hole, because we're actually able to measure stars as they orbit the black hole, very, very close to it. So this is on the order of several solar system size volume of space is kind of in the order of a few times our solar system, and you see stars that are orbiting closed loop orbits very close to the black hole. And until recently, the thought was that it would be impossible to form a star in such an environment, and so they would have to be captured by a cluster of stars comes through the galactic center. The black hole is very massive, and it has a lot of gravity, and so it basically captures some as it goes through, and that was the standard model. However, the strange thing about these stars is they're all very similar, and then as people look further, and they look further out, they found two other disks of stars. These are random orientation, so if they look at all the stars in orbit very close to the black hole, they're kind of all different directions, going different, and they're not in a disk. However, if you go a factor of 10 or so out from here, there are two disks at two different inclinations, and when you see disks of stars, it really suggests that they're formed somehow together in a coherent pattern. And that was very perplexing to the scientists, because they understand is how do the disks get there. So what we did was this image at the top is sort of the image I'll talk about most. It shows the inner parsec of the galactic center, and a parsec, just to give you a sense of scale, is roughly the distance between us and the nearest star. And in our neck of the woods, which is kind of the boonies as far as the galaxy is concerned, there's like a few stars in that volume of space. In the galactic center, there's probably, we know of hundreds of stars, and there's probably many more of lower mass that we don't see. So it's a really densely packed area. In green, you see this thing we call a mini spiral. This is a spiral of ionized gas that is hot gas that we think is being stripped off of the molecular cloud that's further out. The blue in this image is dense molecular gas that formed a ring, and this information was known before. However, what ALMA adds is the red part of that image, which are these clumps of emission in various locations, some of which are inside this dense molecular ring. So the idea in the past was that maybe stars were formed in the molecular ring or outside, but people couldn't understand how you could ever get dense cold molecular gas very close to the black hole, especially as people started seeing these massive stars in the galactic center, which have strong winds, lots of ultraviolet radiation, and that they think that would disrupt any molecular cloud that would come close. And molecular clouds are the seeds, the material that stars are formed out of. So when ALMA detected molecular gas in small, compact clumps inside the circumnuclear ring, which is again the blue ring at the top, it was very exciting to us, because it gave us a clue as to how the stars were formed. So this plot shows for three of those clumps what's called the spectra of the emission, and the spectrum in all fields of astronomy is essentially you look at a position in the sky, and you're measuring the speed at which gas is moving toward or away from us, and it takes a little bit of wrapping your head around to unwind this to understand a three-dimensional structure. But one way that you get wide spectra is if something is expanding. So the idea is it's small because it's so distant from you, and so the angular diameter is relatively small, and so its rate of expansion is not, you're not able to see something get bigger with time, because it would take too long, and it's actually happening all within a very small area of the sky. However, the fact that gas is moving toward or away from you, you can measure that simultaneously with a single observation. So when you see wide lines like this, these are called wings, where the edge of the of the curve goes has some wider extent. One of the ways you get that is if you have an outflow, a strong outflow of material that's leaving that gas, that central gas. This is another plot of other clumps of gas. These are all the clumps in the center, but these are 8 other spectra. If you in the other plot, they were 100 or more kilometers per second wide. These are somewhat more narrower at 20 or so kilometers per second wide. The widest ones are really indicative of outflows. They're very difficult to explain unless they're somehow blown winds that are blowing or jets that are blowing holes through their environment. And so, however, these are somewhat narrower, and so younger stages before that it's called a young stellar object or YSO phase, where you have strong outflows, and some of these are collimated jets. And again, the strange thing was, and the kind of surprise from the observational perspective was, how can you form these within such a strong gravitational potential? Because the idea is that the black hole is massive, so the same force that causes the lapping of waves on the shores here is the tidal effect from the moon, right? It sloshes the little bit of water that's on the surface of our planet around, because some parts of the planet of that water are pulled towards the moon, and as the moon orbits, it kind of follows that orbit. However, you can imagine the effect of what we weren't orbiting the moon, but we were orbiting something that was millions of times the mass of the sun. Those tidal effects would be extreme, and you'd imagine that would jumble up the gas into a point where you don't have the standard theory of collapse happening in a very gentle way. So it means that gas can exist. Not only is it strange that dense gas can exist so close to the black hole, but also that it stays coherent and stays in a form where it can actually collapse under its own self-gravity and form stars without these tidal effects screwing up the whole process. So those are two kind of very surprising results that happened, that came out of these ALMA observations, and we're now trying to understand it. So this image shows 2 of the clumps shown in the contour plot on top of these 2 crosses. So the crosses are locations from another telescope in Chile called the VLT, Very Large Telescope. Astronomers have horrible names for telescopes. The Very Large Array, Very Large Telescope. So we actually need to have some sort of PR person come up with a better name for this stuff. But VLT is a very powerful optical telescope, and also near-infrared. So these are near-infrared positions of excesses in which suggests that there's a compact continuum object, which means that it's basically a hot embedded object, and it's very close to these clumps. I should also mention that the molecular line that we're looking at is called silicon oxide, or SiO, and the silicon, which is again the component of the grains that are forming the gas, the sand outside the hotel here. It's the same material. But in this case, they're significantly smaller. So the dust grains here are really tiny. But when you have star formation, basically you have these dust grains that are made of silicon. They start giving out they start turning the silicon from a solid phase into a gas phase, and then this binds to oxygen and becomes visible through this. And that's the radiation you were seeing. Those spectral lines were fingerprints of that particular molecule. And the fact that the clumps of where the silicon oxide is found, and I should also mention that in spectroscopy, you're always looking at one excitation level relative to another. So these are highly excited excitations from SiO 5 to 4, and to get those to that level, you have to have fairly high temperatures. And all of this is consistent with what happens in the young phase of star formation, when things are collapsing down, and then there are winds that are blowing out. So at some level, the more we look into these features, what we see are what would actually look like normal stellar evolution, or early phases of stellar evolution, stellar birth, that we might see near our sun, but we see them instead of in the area of the galaxy where there's lots of gas and there's lots of room and there's lots of time without any other large disruptions for things to collapse. Instead of that, we're seeing this happen in the most extreme location in our galaxy, right next to this supermassive black hole. So again, there's lots of research to be done to understand that. And this slide here is essentially looking at the ratio of, to basically understand, are the stars that are formed in this process here significantly different than the sort of stars that are formed in the plane of our galaxy. And so what you see here are on the y-axis, this is a ratio of this line luminosity, the peak, the line strength that you're seeing in this SIO line relative to the it's scaled by a solar luminosities, and this is and then on the x-axis you're seeing the width of the line. And I mentioned that some of those lines were wide, so that these 3 points over here represent the wide lines that were more than 100 kilometers per second wide, and then the points to the left-hand side, the filled-in circles, represent the narrower line widths of about 10 or 20 kilometers per second, or 10 to 50 kilometers per second. And essentially, we compared that to disks in the plane of the galaxy, again near where we are, and said, are these typical? Are these unusual? And essentially, the squares, the unfilled squares at the top, represent disk star formation numbers that are for high mass stars. So these are stars that are 4 to plus solar masses, and then the ones in the diamonds, unfilled diamonds in the bottom, are low mass star formations. So the stars that we're seeing, we think are being formed in the galactic center, are actually in an intermediate mass, which is exactly in between these two different populations. And when I mentioned those stars, that one plot that I showed where the stars orbiting the black hole, those stars are kind of the upper end of this distribution. So everything seems to fit together, that the stars that we're seeing in very early, kind of nascent, kind of baby stages of star formation are similar to the stars we are formed out in the disk of the galaxy. Again, we might have expected that even though there's something can be formed very close to the black hole, it would be different. But it turns out they're actually quite similar, and moreover, that the stars the masses of those stars that were being formed are similar to the masses of similar stars in the plane of our galaxy. So at some level, we look at the black hole, the center of the galaxy, and we say, oh, this must be really an extreme, crazy environment. It must change. We have to have different physics that goes on there. But actually, the data from ALMA really suggests that at some level, kind of semi-ordinary star formation is happening even in this crazy environment. Now, most of these, I should mention that this is from an early verification data from ALMA, which is a couple years old, and ALMA is constantly being upgraded and is near the end of that process, and soon we'll have many times more telescopes than were available for this observation. So our plan is to go and reobserve it, look for higher resolution knots, and try to confirm this and see what's going on. So in conclusion, the idea is that the molecular ring of in the center of the galaxy is really is not devoid of molecular gas. Somehow dense gas clumps can survive coming close to the black hole without being disrupted or blown by the winds of those stars. The star formation is taking place very close to the supermassive black hole. That the gravitational potential and the tidal effects of a black hole doesn't suppress star formation. The line widths of those stars are consistent with kind of semi-ordinary young stellar objects that we might see in other places in the galaxy, like around the sun. We believe that the stars, when they're fully formed, this will be sometime in the future, will be of the same this kind of intermediate mass stars of the type that we see in the galactic center and also in the field, but a lot of stars that are larger mass in the galactic center, and then the ranges of stars, the ages of the stars that we saw are exactly the same age ranges that we see in the galactic center. And then also, I'll conclude just by saying that these are all kind of tentative results. One of the things that I mentioned was that the resolution is critical. If these things are outflows, one of the things you see besides the Doppler shifts, which give you the broad line widths, are also, at some level, you can see elongation coming from the fact that this jet from these outflows can be gives you an elongated source. And at this resolution, we're just barely able to resolve that. And given more sensitivity and more resolution, we can nail that down to find out if there's a jet axis which is consistent with the kinematics that we see, or the gas motions that we see. And the other thing about this is the kind of the thing that ties us back to the whole galactic story is understanding the efficiency at which stars convert. So stars, essentially gas gets converted into stars, and we have a fairly good idea of what that efficiency is in the field of our galaxy, but we have no idea what that is, because we didn't even know that process took place near a black hole. And if that process is actually efficient, then that would actually absorb a lot of gas, because it would turn gas into stars at a fairly high rate. However, it might be that these are just a few and happen very rarely, and this efficiency is really low. And so, but we don't know, because we've only sampled a small field, and we need more resolution and more sensitivity to look for even more compact, even earlier stages of star formation. So, ALMA has been a great telescope so far in its short lifetime, and me and my colleagues in this particular field, and I think the entire astronomy community are really looking forward to using it when it gets fully up to speed with the maximum number of antennas and so forth. So I guess I'll stop here, and if you have any questions, I'll be happy to answer them.
Questions?
I heard that maybe as much as 80% of the stars in our galaxy are actually, excuse me, are dwarf stars, M dwarfs and red dwarfs and brown dwarfs.
Right.
Would you actually see those? Would you have the resolution to see those in the galactic center?
That's a great question. So the question was that stars are almost never, actually we don't, the current theory now is stars are never formed as a single entity. They're always formed as groups. And those groups have some distribution of sizes, from big massive stars to low mass stars. And the idea is that if a group of stars are formed, how many low mass stars versus high mass stars? And the general idea is that most of the stars that are formed are less massive than the sun, for instance. So, and then only a small fraction are in the high mass range. It's called the initial mass function of a cluster. So. One of the things that we think that is unusual about the galactic center that we need to probe, and that, is that when we look at the stars in the galactic center, they do in the two distributions that we see, these ring-like structures, and we look at the stars, there are many more high mass stars than low mass stars. So that is an unusual thing, because in the disk of the galaxy, it's the other way around. It's called a top-heavy IMF in the galactic centers, which is unusual. So so you're absolutely right that we need. It's possible when these clusters, that these stars, when they're formed, are formed, and they're low mass companions to them, that we're just not able to see because of, again, sensitivity. These are, 4 or 5 sigma detections, and so things that were smaller and less and had less flux would be impossible to see. So. Again, that's the thing. We're going to higher sensitivity is probably the thing that helps you more than anything else. And that would be another thing that we would do with new data sets with a fully fleshed out ALMA. That's a great point.
Thank you.
Yeah, thank you very much for this wonderful talk. ALMA is producing a fairly large amount of data, like per day. I was wondering, how do you treat the picture, the data you're getting? So I guess that there is a lot of challenges from the computational point of view on how to treat and transform the picture you're getting. Can you tell us a bit more about that?
So you're saying that the data rates from the telescope, or the...
No, the picture from ALMA is about like 1 gigabyte. I heard about that. So I was wondering, like, how do you manipulate those pictures? Because,
Yeah, that's a
actually
good question.
large,
So the data from ALMA and almost all radio synthesis telescopes doesn't directly come as images. So it comes, these telescopes that are where you have separate dishes over large areas, they acquire data before it gets turned into an image. And so, but it's kind of even worse than the image case, because in the image case, if we were just given images that were perfect, it would be great. But in the case of every radiosynthesis telescope, you oftentimes want to go back to the original data, and you have to worry about bad data. That's one of the things called flagging. So you can have basically outliers of data before the imaging process will screw up the imaging process in a big way. So you have to, so these data, moving the data around and dealing with the data is a huge problem, and will become a bigger problem as you put more telescopes online. And also the other part of it is, I mentioned a picture that had the large spectra on the right-hand side. ALMA inherently has a huge bandwidth with a lot of individual channels. And so you don't see, when you do form the image, you don't form one image, you form a cube where it's made up of individual planes. And so those cubes can be enormous. Actually, the image cubes can be much larger than the visibility data that was used to create them, depending upon how you scale it. So right now, it's manageable, but I think it's actually one of the challenges of radio astronomy specifically, because all of our telescopes in radio astronomy are becoming more and more powerful, which means they're acquiring data at a higher and higher rate. And I have this problem myself, where we just built a server at Northwestern, and I spent $5,000 on it or whatever, so it has a fair amount of rated fast disks, and just making one image takes a couple days. And if you screw up at one parameter, then you have to wait another couple days to make another image, and maybe you want to tweak something or flag a data set, and it becomes a human, interacting with human time. It just doesn't work when things happen over weeks and months. So it is a place where I think work needs to be done on the image processing side to make it more of a service that you can add components to. I think it's a cloud-capable sort of solution where you can, the idea of the cloud where you apply resources when you need it and then release them when you don't, makes a lot of sense in this case. But right now, the tools aren't designed to live in the cloud, and they're designed to live on workstations. So I think it's an opportunity for partnership between kind of the computer science and radio astronomy to make these cloud-enabled so they can actually be as services that you call upon when you need them. But right now, that is a huge problem and slows down the interpretation of the data for sure.
Thank you.
Yeah, welcome.
Time for one more question. Okay.
Okay,
Thank you.
thanks.
Thank you very much, and it's an honor for me to be here. My name is Juan Rodrigo Cortés. I am ALMA operation astronomer working for NRIO, and as I'm new today, I am a data scientist, and I'm going to talk to you about a little bit of ALMA data visualization, what we call a kind of a 3D view of the cool universe. I would like to apologize because I'm in a Microsoft meeting and I'm using a Mac, and I'm using PowerPoint on it and a legal copy, which is good. So I pay for it. Okay. Thanks to Doug, we know a little bit what is ALMA, but very fast. Well, ALMA is an interferometer composed by 66 antennas, 54 antennas of 12 meters, and 12 antennas of 7 meters. And ALMA actually is the equivalent to the Hubble Space Telescope and the BLT, but in millimeter astronomy. And it has similar or better resolution and sensitivity. You can see here, well, it doesn't look so well, but this is the HST resolution, and this is ALMA. And ALMA is about factor 10 better than the HST. And ALMA is bringing a revolution in millimeter astronomy. What we build ALMA, we build it basically for detect carbon monoxide and the ion of carbon in Milky Way-like galaxies. The redshift equals 3 in less than 24 hours. In that time when we were planning ALMA, that looks impressive. And also for doing imaging gas kinematics in protoplanetary disk. Of course, that's why we build ALMA, but it's It's different what you build and what finally you are getting. And for building a telescope that can do that, we required a large collecting area, actually about almost 10,000 square meters of collecting area. That means a large amount of antenna. That's why ALMA has 66 antennas. And also because we want to detect CO and another higher transition of CO and this ion of carbon, and that's continuing in high redshift galaxies, so galaxies that were formed, billions of years ago. We need an adequate site where the transparency of the atmosphere is pretty good. So that's why we will ALMA in Chile, because we had this kind of sites. And we choose the windows, which ALMA can see in the areas where the atmosphere is transparent. So we design our view of ALMA to be the most efficient possible toward the sky. Don't talk about also fidelity. Why we need fidelity? Because fidelity allows us to map in structures with a great detail and a great confidence. But that requires what we call a good UV coverage. This is what we call the UV plane, and each dot here represents a pair of antennas. And if you are helped a little bit by the air rotation, you start to cover all the planes. So you have recovering almost all the spatial information. So you can, after, synthesize the image and do a nice image on a nice data cube, as Doug talked before. For this, we need 66 antennas. That means that we need about 2,150 baselines. So that is a lot. And also, because we require going as deep as fine as higher resolution to map, for example, the mass, allow black holes or discriminate galaxies in deep images, you need a precise imaging, so a very high spatial resolution. That means that you have to reconfigure your array. And for that reason, we had to build these two, big trucks that take each antenna and move it around between 1 kilometer to 16 kilometers in order to give us the spatial resolution that we need. Briefly, how ALMA works. Basically, what we have here is our antenna that receives the astronomical signal is getting in the receiver where it's amplified. It goes to a part that we call the back end where we digitalize the image. We send it to a central computer that is called the correlator, which receives the signals of every antenna. And as the name said, it correlates the signals to make it will be like a one telescope. And then we package the data and we send it to our archives for data reduction and analysis. Okay, how we use visualization in ALMA. Okay, what we get after the data is getting out of the correlator and then set down in the control room. And okay, let me see what I want to see what we get. What we get the following. Okay, what we get basically is what we call fringes. Fringes is information regarding the correlation, this correlated signal between two antennas and the phase. Well, it doesn't look too well, but here is the phase, and this is the correlated signal. This is the autocorrelation for each antenna. So you see nothing here, but if you correlate, you start to see something that we call a line. This is channels, and this is amplitude in correlation. And this you have for every antenna pair. So you had 4 quantities: autocorrelation for both antennas, the cross-correlation amplitude, and the cross-correlation phase. Per antenna pairs, and of course per polarization, because we observe until 4 polarization. So you can start to guess that is a massive amount of data that we are receiving. And also we are receiving other data that we call metadata. That's information regarding receiver noise, phase fluctuation, that is atmosphere fluctuation, the pointing of antennas, how good antenna points, focus, delays, weather information, all of that. Well, as I said before, we have a lot of antennas, so that's mean a lot of antenna pairs. All interferometers, like OBRO, VIMA, have about 12 antennas. I worked with Obro before for my PhD, so there were 7 antennas. And that's been 21 antenna pairs. That's not too much. So I can see these plots and look at, okay, yeah, the signal looks good in every antenna pair. But now ALMA has 50 antennas. That means there is 1,200 antenna pairs. That's a lot. And when ALMA has 66 antennas, we will have more than 2,000 antenna pairs. What we have here is a plot where in this image, you have here the antenna names, all the antennas, and the signal-to-noise ratio. That means the signal-to-noise ratio of each of these amplitude cross-correlation. And that's a way to visualizing the fringes. But of course, here it just is for making simple, because we had much more information. Actually, for each point of here, you had one of these, one of these, one of these, one of this, and four polarizations, so multiplied by 4. So that means an amazing amount of data, and it's pretty hard to, for example, if you had a problem in one antenna pair, in one band, in one specific polarization, to look at it, okay, and see and visualize the problem. Let's talk about a little bit the typical unreduced data. That astronomers use this term data reduction, that because we reduce the size of the data. Well, an unreduced data, it has per antenna pair, amplitude, phase versus frequency, time, polarization per object. Because we not only observe one object, we can observe several objects plus the calibrators. If we have 25 antennas, this is more or less what is cycle 1, what the capabilities that we are offering for ALMA, with ALMA for the community now. That's mean 300 antenna pairs. Let's do some simple exercise. For each pair, per hour of observing, and I integrate 6 seconds, since I have 600 chunk of time, I have about full operation, 66 antennas. Then you have not 300 antenna pairs, you have more than 2,000 antenna pairs. Then this start to escalate, and also you had 4 polarization. So you had 300 gigabytes. That's mean among 7 terabytes per night. If the project includes more time, and for example, you do a mosaic or something more fancy, an fancy observing mode, or you need more sampling of time, a variability much smaller, you can have at the end in your project, as astronomer, about sizes of your project about terabytes. So that's complicated. You take this data, the unreduced data, and you had to use the ALMA pipeline on the ALMA reduction system. So you calibrate the data. After that, you do what we call the inverse Fourier transform, and then you take out the contribution of the antenna beam, or the beam pattern of the interferometer, and you use a method for taking out that we call the convolution. For that, we have a special reduction package that is called CASA, and actually it's written in C++, and for practical reasons, we brought it in Python. And this is what you need to solve. This is what you observe. That is called visibility. That is in Fourier space. And this is what you want, this is the image. And you had to solve all these terms for each antenna pair. So you had at the end matrices. So it's a complicated problem, but we know how to do it. Radio Astronomer has been doing this for the last 40 years. The problem for ALMA is that you had a lot of pairs. And then you had your reduced data. In your reduced data, you have the magic that for something so ugly as this, phase versus frequency, you have something much beautiful. That this is a M100 galaxy. You see the center, spiral arms, much more beautiful. So basically, from something so horrible like having amplitude phase versus frequency time polarization, you ended up with something that you can word that is flux versus frequency or velocity or wavelength or color, whatever you prefer to call it, by two special coordinates that we call in astronomy right ascension and declination. So, and the data could be much smaller. For example, for cycle 0 data, or for this data actually, when M100 is an image of 300 by 300 pixels. There's only 140 channels, one polarization. There is more or less 14 megabytes, so the data was actually reduced in size. But if I use full spectral resolution, so I use the 3,000 channels, the data escalate to 1.4 gigabytes. And if I did a mosaic, and I have 150 pointings that we are giving now as a capability, you can have something of 200 gigabytes or even larger. And what is the final product? Talk a little bit about that, is what we call a data cube. A data cube basically is flux or intensity, if you prefer, in function of two spatial coordinates, x and y, what we call right ascension and declination, and a third axis that is velocity or frequency. The problem of data cubes are kind of hard to visualize. And astronomers, we are kind of stubborn people and don't like too much 3D stuff. And we like to use slices. We slice a lot. So what kind of slices do we do? Okay, this is a representation of an overall data cube. You have for each position a spectra, and you can see the entire information. But this is not too practical for ALMA because we had too many points. So that's no good for ALMA. Another is what we call the channel map. So you take, per each velocity, per each channel, you produce an image, like a slice, and you put it in like this panel. And this is a way to visualize, and you can see more or less some features and how, for example, the structure changes with velocity, and you can derive some conclusions from that. Another way of visualization is what we call the position velocity diagrams, that you do your data cube, and you take the data cube and start to do slices and integrate to a special direction. So, for example, I do a cut here, and then I see how it's changed in velocity, how is intensity in velocity versus, in this case, must be the major axis, here the minor axis, and I can see there is some kind of, I wouldn't say rotation, but some kind of motion in the minor axis of this object that is actually a galaxy. And there is, of course, more physical representation, and again, is collapsing the cube in some clever way that we call the moment maps. If you had a data cube that's dependent of the two spatial coordinates and velocity, and you had a velocity beam, you can have an intensity by just adding, and then you have the intensity maps. Or you can take the velocity beam and do averaging, but weighted by flux, and that's produced what we call a velocity field. And you can do the same, but after having the moment WAMP on the velocity field, but to the square, and this is like a dispersion, and actually we call that the velocity dispersion. That gives you some idea of the turbulence. And then we can play with that, with this map. Okay, I had the velocity, I had the dispersion. If I have the intensity, in astronomy, I can start to take models and get information out of it. For example, in stellar models, I used to work in dynamical stellar models. I used to work for my thesis with Eduardo. What you get from two-dimensional quantities like intensity, velocity, and this velocity dispersion, you start to get three-dimensional quantities like the density, the gravitational potential, the velocity structures. So basically, from a 3D space, you start to get a six-dimensional space that the physics, call the phase space. Coming back to ALMA, what visualization tools we have for our data? we have something that is called the CASA viewer. The CASA viewer do maps, contour maps, raster maps like this, and some vector maps, and you can do, of course, slices, because we like to do slices. Channel maps. This is the case of position velocity diagram. I can take one slide here. Okay, I use the tool. Okay, I think that this is a galaxy. This is the major axis, and I see, okay, this is the position velocity. Position with respect to the center and the velocity. And I can tell a lot about that, like this is a solid body rotation in the galaxy, and here start the dark matter dominated. But well, I know what I'm seeing. For that reason, I can tell you that. And if you like more or less movies, you can do a movie, and you see the plane channel by channel. So remember that we have a data cube. So here you're watching the slices of the data cube. So that is another way that we can visualize data. Okay, but this is too boring. So let's start to see how we visualize real, published ALMA data. This is a pretty nice result that was published by Merker in Nature in 2012. This is a star, an RGB star, an AGB star, that present this structure when you do the moment zero. It's kind of rings and spiral pattern. And if you do the channel map, you see that the emission changes with velocity. So it starts to be bigger, 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 have just this kind of ring, and then kind of collapse. So this is interesting. And what is the interpretation? If you start to do a movie of the channel maps, you realize when you explore the data that actually this is a expanding shell, a spherical shell of material that is expanding, that the star is ejecting. So even if from the velocity and the size, you can tell how much time ago the stars start to have this process. But basically, this is a movie of a channel map. So it's nice, and it helps the interpretation. This is another case, and this is a Chilean investigation that's done by Casasut et al. From Universidad de Chile. That's published also in Nature. It's a protoplanetary disk with this horrible name that I'm not there to pronounce. And you have, this is the continuum image, what is just the dust, and here are planets that are forming. This is the carbon monoxide. You have kind of a ring of carbon monoxide. And if you believe me there is, according to the authors, there is a pair of filaments that are like streams of gas that are going to the central star, and probably are due to the formation of two giant planets. But if you see just only this plot, that's not obvious at all. You can see easily that just doing slicing or doing averaging doesn't work too well. But you can play with some other tools like Blender, and this is something done by my colleague Brian Ken from NRAO. He took the data from Casasut et al. And he put it on Blender. There is a paper there, so you can see that paper and contact Brian. And then we can clearly see the stream of gas. Okay, this is velocity, and this is the two special directions. And you see the donut here, the same stuff. And look at these filaments. We played it again to be more clear. So within the border, and then going toward the center. So this velocity is increasing this way. So that means that the gas here is flowing toward the center, and the other gas is flowing toward the center. So I show it again. I think that this is a pretty nice use of the 3D view. So you can really tell what is going on. Not from this, but from this. That makes a big difference. Another example is, this is the case of NGC 253. That's the Coulter galaxy. And this was done by Alberto Volato. And what Alberto Volato see is a lot of molecular gas in the center of this galaxy. And here you have an outflow. of gas that's going out from the galaxy disk. And you have a visualization that also is in 3 dimensions. Velocity is in the vertical axis, and you can see the structure, the velocity structure of the gas inside the galaxy. Here we are in the minor axis of the galaxies, the major axis of the galaxies, and you see a lot of high velocity structures that probably due to the outflow. Some challenges about data visualization. Well, displaying the data is not good enough. You see nice pictures, nice movies, but actually it's hard to interpret those pictures of those movies. So something that we need as astronomers is somehow integrate physical models to be included in our viewers. So that's going to help us in understanding of what we are seeing. And also, as you see before, sometimes slides are not good enough. And this is a good case that the protoplanetary disk that we saw before, where actually 3D imaging can really help in the data interpretation. And the actual viewers that we use for data visualization doesn't handle 3D capabilities. We can use other tools like Blender, but they are hard to use for astronomers. We are very lazy. We don't read manuals, and we don't want to spend too much time on it. So we may need dedicated, easy to use, intuitive 3D, I put plus because time is also important, 3D tools to allow us to visualize our data. That's mean having a good space phase visualization. Another problem is the data size, data cube size. We can easily reach 200 gigabytes and 1 terabyte full resolution. That gives us memory problems in machines like this, especially on Macs. So that's also a challenge. Another challenge is that ALMA has a lot of sensitivity. That means the detection of unknown lines. So we have a forest of lines. This is Orion, and here you see a spectra that's crowded of lines. So how we blend this line? How we identify this line? We had to cross-check with line catalogs, like a Splatalog that is developed by NRAO. But doing by eye, it really takes too much time. And with the capabilities of ALMA, you had 15,000 channels. It's too much. So how can we do it? Also, another challenge is the integration with virtual astronomical observatories. That's something that we had to consider, and I had to mention a little bit. There is a Chilean effort that is Chivo. Some people from Chivo is here that is trying to get ALMA and all the data that we are getting in Chilean and telescope in one platform, and people can do some data mining on it. So as a summary, well, ALMA is bringing a revolution in millimeter and submillimeter astronomy, but we had too many antennas, too many antenna pairs. That means a massive amount of data, so several terabytes per night. And data cubes, depending, can be from megabytes to terabytes. It depends on how picky are you in the resolution. And we have different challenges. Slices are not good enough, and we need some more intelligent 3D visualization, include physical models, dedicated 3D tools that done by 4 astronomers that we are lazy, some integration with virtual observatory and catalog support in order to improve what is called the data sharing and the data mining, that is the new astronomy that's coming out. Of course, efficient memory usage, because we wanted to do it in our laptops and don't have a cluster for doing that. So thank you very much.
Thank you very much for a very extensive and clear presentation of how difficult it is to look and analyze this data. Questions?
Hi. Do you get an estimate on how long it takes to produce these images, like the 3D Blender models and all those sort of things?
Well, I can tell you for experience. I mean, basically, right now, with the data that we're taking, it it doesn't spend too much time like in doing the convolution. That is the most expensive in computing power. We are spending like 1 hour. But for telling the truth, because we are using a cluster, we are not using this laptop. That is this is the capabilities of the cluster. Sorry. So in that cluster, takes like 1 hour in doing the convolution. But the problem is that in the future we are having more antennas, and that means that the size of the data is bigger. So then we have to consider another options. More than a cluster, you have the way to you do the data reduction. So maybe parallelization, things like that.
Anybody else? Yes.
So it seems to me, and you kind of laid this out, there are kind of two ways to deal with this. One is to build into something like Casa Viewer a 3D, some sort of 3D rendering and that sort of thing. Or another way is to make an interface so that you can easily go to an external piece of software, whether it's Blender or something else. Yeah. Do you have a sense of, well, which one is more tractable? Which one would be a better direction to go?
Oh, that's a good question. I would say that as an end user, I would like to use something easier. Blender is a nice tool. It's nice for animation. You can do very nice animation, but it takes time for us to learn. So it will be easier, to go there. Okay, I got my data cube voxel, something like that, and produce a nice render of it. So I will go for trying to do a small, easy-to-use applications for doing that. Although I am aware that is not the priority for the community, because also these data sets are very big, so the memory issue is a bigger priority than having a nice 3D visualization. But 3D visualization in the kind of data that we are getting in ALMA and the complexity of the data really can help if you know how to do it for your data interpretation.
Who can use the data that you are collecting with ALMA?
Well, that's a good question. Okay. So, first of all, we had something called the proprietary time. That is 1 year. 1 year only that the data can be used, the API that proposed the project. After a year, the data is public. That means that any person that is registered in the ALMA website, in the ALMA Science Archive, can take the data and do whatever he wants with it. Actually, but the owner of the data is ALMA. But anyone that is registered after a year can make use of the data.
And can they use also your tools that you developed, the CASA software?
It's totally free and open. Yep.
Anybody else?
When you say that this is a public data, what do you mean? Is raw data or the feeds?
You mean the delivery? What we deliver basically is the raw data that is in a format called ASTM, the feeds files, that is the end product, that is 4D cubes or 2D images, the logs, the scripts that we use, the calibration tables, the quality assurance reports. So basically we deliver everything. So you can take the data and reproduce the data reduction and improve it, of course.
Okay. Thank you very much.
Okay, so I'm the same person, but a different talk. I was supposed to be here, or another person was supposed to be here from our group, Jonathan Fay, who's the principal architect of Worldwide Telescope. I kind of wear two hats. One of my hats is research, the other hat is outreach and visualization. and actually Juan's talk was a great transition into a Microsoft research project called Worldwide Telescope, which actually has a lot of the characteristics of the sort of tools that I think need to be out there for the astronomy community for the analysis phase. And Tony mentioned some of the motivations behind Worldwide Telescope. Essentially, there was this huge data project called the Sloan Digital Sky Survey that was going to require a huge amount of data, and Jim Gray, this brilliant computer scientist at Microsoft Research, helped figure out the data set and data architecture for it. And then it became obvious, and it was his idea to think of a virtual way to explore those data as well as all other astronomy data in a very open manner, the same way that the internet opened, or a web browser opened the World Wide Web to people. The Worldwide Telescope was meant to open up astronomy for the public. So initially, this was launched in 2008, and initially, because of we don't mention it, but the sort of things that Juan and I observe, you can sort of think of as pasted up onto the night sky. They're at a distance, but the distance we actually see them just as paintings on the top of a celestial sphere. And so the first way that Worldwide Telescope worked was to represent that night sky. So the things that Tony mentioned were the ability to change images, to change the background images, so this viewer is just a screenshot of the application, and it allows you to choose what background wavelength you're looking at. So you can look at the sky in optical wavelengths, which is how we normally look. But let's say we want to compare it to what the dust emission, and dust absorbs in the optical and emits in infrared. So there we'd want to use an infrared sky. And then we can overlay a high resolution image on top of it. And that ability to crossfade between two images is incredibly powerful from an observational astronomy point of view. It's something we do all the time. A lot of the plots that I showed in my earlier talk, where you had a background image with a contour plot on top, was simply a poor man's way of doing that, where you kind of do, but be able to interactively do this is much more powerful. So that was done at launch, and obviously it got improved with improved data sets and rendering. The next thing that got added to Worldwide Telescope was the ability to visualize planets and 3D structures. So it actually has a very powerful rendering engine that can show the surfaces of planets, all the way from the surfaces of planets. You can pull out and see them as spheres with a high resolution texture on top of the sphere. Pull out even further and see them as points on orbital lines. You can move time forward and backward to see the orbits as they would actually move. If you wanted to simulate an eclipse or find out when certain planets were aligned, or when something was in view of a telescope or something, you could actually put that in the system. And so that was the next phase in this 3D, what we call solar system view, because Worldwide Telescope is very data driven. It's driven by the data that's out there. So there's a ton of data in the sky. These terabytes per night or whatever are going to come from ALMA are just one observatory, and there's many observatories at that level, and so those are all sky views. We have orbital satellites around Saturn, Mercury, the Moon, Mars. There's one that's going to fly by Pluto, and so we're acquiring and of course the Earth, many Earth-based Earth-observing satellites looking down at the Earth, and all of these data exist out there as layers that we can lay on top of these bodies. So that 3D solar system mode gives you a way into all of that. So kind of skip forward to this year. So at the American Astronomical Society meeting in Washington, D.C., in January, the team announced Worldwide Telescope 5.0, and so it's the 5th year anniversary of the tool, and so some of the features that were added in order to make that work were really take it to a point where it can be used for very cinematic presentations. So similar to what Juan was talking about with Blender. A lot of that capability can be done here, so we should actually sit down and talk about that, because I think there are some things that this could solve with a little bit of work. But one of the things that it has the ability to do, which Blender does too, is this thing called a timeline editor. So if you want to have, when what Juan showed in that visualization, you saw a rotating cube. You were basically, you set certain point camera views, and then you rotate and you say it's going to be here at this time, here at that time, here at that time, and you can change those keyframes, and that's exactly what you can do here. So this is very similar to a sophisticated video editing suite, but now it's in a free piece of software that's available to the public or professional astronomers or schools or to anybody else. So this timeline editor really makes very fine-grained, frame-by-frame visualization and control possible. Another capability that adds a tremendous amount of power is this ability to load in 3D models. So we can pull in any sort of 3D model into the system. You have to put it into a reference frame and stick it in a particular place in space. So some things like spacecraft, that's very natural. There are ways you can go to NASA or ESA and find out where a representation of the orbital of the orbits of these things. So, for instance, this is the International Space Station, and it's included with Worldwide Telescope, and we include the orbital parameters to put it where it is at any time and any point in time. So, if you wanted to look at it where it is today, I could fire it up, and we could just look at it and say it's over right now. It's over, wherever it is. But we could also put whatever telescope you wanted. So. I'm actually working with ALMA to get 3D models of the vertex dishes, so we can stick them at the locations on the ground, and people could make it would be great PR for ALMA to show a movie pulling back from the Earth all the way to space, or show how reconfigurations work. You can imagine that the thing that one of the powers of ALMA is the ability to move telescopes, but that requires a bunch of still images to represent that, or you could do it in real time with a powerful tool like Worldwide Telescope, which is, from a communication standpoint, very, very powerful. The other thing that is in the new release is this ability to do volumetric atmospheres. So we don't, in volumetrics, we now have, everything's been ported over to DirectX 11, and we use advanced shaders for these things. So in addition to kind of solid body, just kind of images wrapped around height or terrain or texture or height maps, we can also do volumetrics of atmospheres. So here it doesn't represent this projector very well, but the edges of the Earth's atmosphere are actually illuminated as the refraction of light through the atmosphere through a model of the atmosphere. And actually, just as a kind of side story, we had Chris Hatfield, who's a commander of the space station, who was at a conference that we showed this at last month, and he was commander of the space station for 7 months, and we showed him this, and he was quite happy with it. He said, "We've seen it from space, and this is basically the way it looks." So we were very happy to see that representation. And the other powerful thing about Worldwide Telescope is it has a very diverse set of input devices. So you can use an Xbox controller to control it. You can use a Kinect with gestures. You can use it's called a MIDI controller, and so with knobs and physical buttons to do things. So, or you can use head-mounted virtual reality displays. And so all of these are possible ways to interact with the data, and that's built into the system as it is. The other direction that the team has been going is actually to kind of free Worldwide Telescope from the desktop and put it into the web, into the cloud. And so there's now an HTML5 version of Worldwide Telescope that's available. So the top link, and I'll put this to the end of my talk if I have any time. I'll try to do these live. I did see I'll need to check the Ethernet to make sure that I'm getting enough bandwidth to do these, because the Worldwide Telescope is inherently a internet-enabled application, whether it's running on a desktop or in the cloud. It doesn't hold it holds just a minimal amount of data locally, because the idea is that data are curated by the people who acquire the data. So if we were to make a feed for ALMA, for instance, ALMA would hold the repository, we'd point to it, and that way, if they reprocess the data and reran the pipeline, any user would get the newest data when they got it versus getting whatever version of data there was. and then let's see, is this the, I'm trying to use a laser pointer, but anyway, the second one is an interactive on the spectrum. So it comes out. Oh, there it is. Okay. So the second one is to interact with the spectrum. The thing that you can do in the web client that even makes it in some ways more powerful than the desktop client is you can create web experiences that are very customized and filter the interface to see only the things you want to see. Yeah, I found the button. Yeah. So in this Spectrum Interactive that the team put together, you can actually use one slider to slide through all the wavelengths of the background sky, from gamma rays to radio waves, and just see it as a smooth transition. And that's actually impossible in the client. In the client, that would take a whole series of keystrokes, whereas in the web, we've used HTML5 controls to create a slider that does that automatically. So if you wanted for a talk or for a website, one of the things we're looking for is to make a case to embed this into the process of science, and I'll get to that in a second. And sometimes the science you want to tell, the science story you want to tell, you want to kind of take away all the things except for the one topic that you want to communicate, and this can be done quite naturally with the web client. There's also another one called Great Observatories, and these are all, by the way, on the website. These first three are on the Microsoft's website. And this is a kind of an overview of NASA's Great Observatories program, all the great space observatories, including the Hubble Space Telescope. And then one thing that I think is very powerful is this ability to give this control, not to hold it to Worldwide Telescope team, but to give it to other people. And so we had a very successful press release at the TED conference in Vancouver in March, where we work with NASA. They wanted to have a press release of a new data set that they had acquired, where they had used a telescope, an infrared telescope called Spitzer, to acquire this very high resolution strip of data across the entire plane of the galaxy. And so they announced it at the TED conference, and they made an interactive viewer that was available online, and then they actually curated the viewer. So the viewer was on Spitzer's site. It turns out some magazines took it as well, so it was available at various other locations. And the team is working hard to make this as easy as possible for other people to use. So the idea is that people who do press releases, instead of having a single static image and trying to tell a story with that plus words, you can have an interactive image that would look like a static picture. You could print it out and so forth, but if you were in front of a web browser, you could actually zoom in or zoom out. One of the very powerful things in astronomy that most people don't realize is that most of these almost all of the images that Juan was showing and my images are tiny, tiny, tiny fractions of the sky. And as an astronomer, especially as a radio astronomer, I don't know hardly the night. Actually, through Worldwide Telescope, I know a little bit more about the night sky, but I'm really bad about knowing constellations. But it makes it really easy because I can just say, this is where I'm at, and then I pull back, and then eventually I see where that object is embedded in the sky that, well, maybe I'm not familiar with, but maybe some of you are familiar with, with constellations. I also live in Chicago, which I can't see the night sky, so that makes it kind of irrelevant. But I can see where it is, and that's a very powerful way to have context, to ground a very distant, strange-looking thing to something you can see with your own eyes. So these are the capabilities. So how are these capabilities used? And so they're used to support various sorts of activities. One is inquiry-based learning, and this is through a program called Worldwide Telescope Ambassadors Program. This is out of Harvard. Another colleague that Tony mentioned, Alyssa Goodman out of Harvard, is a leader of that program. And the idea is that to find ways to use Worldwide Telescope in formal education and to both carry out programs and so forth, but also capture them. So if you've developed a curriculum around using Worldwide Telescope, in one case, there's no reason you can't share that with other people. And so this is a freely available resource to go to the Worldwide Telescope Ambassadors Program website. So if you're not in the areas where these ambassadors live, you can use the resources that they create. And if you are around them, you can actually get them to do professional development with teachers and other people. One of the other things that was a big push for Worldwide Telescope was actually to get into planetarium domes. So Worldwide Telescope, I'll get to the final thing in a little bit, but you can run it on multiple machines and have them coordinated in such a way that they show one seamless image. So the way the most modern planetarium domes work is you want to do a bigger image than just blowing up this. You can imagine this projector is kind of fuzzy enough as it is. If I took this image and made it over an entire hemisphere, it would be very low resolution, right? The angular resolution would be very, very tiny. In order to make that work, you'd have to have multiple projectors projecting different pieces of an image all seen together. And so when you do that, you have problems of storing the data, of latency, a lot of network communication, and so forth. And so all of those were solved by Jonathan last year. And so it was the time when I was at the Adler Planetarium in Chicago, and we installed this on the world's biggest planetarium, which uses 20 projectors to make a larger than 8K by 8K image. One of the largest display systems in the world, and Worldwide Telescope works flawlessly on it. It's a really beautiful system. So, having solved that problem for the highest end user means that now we've made this software available, and now it's installed on several of the high-end systems, but also increasingly on lower and smaller systems, because obviously if you solved it for 20, you can run it on 6 or others. And so the number of eyeballs that have seen Worldwide Telescope, and they may not know it unless they sit and watch the credits, but it's actually driving a large number of planetarium domes in the world. Another audience that we're trying to really tap into is the research audience. People like myself or like Juan and like the people we work with. And so Worldwide Telescope can be used in various ways to connect with research. This idea that Juan had of a real 3D tool is something we should explore, because that would be something we could probably do. But currently, there has a lot of interesting capabilities, like what's called a finder scope. So I can right-click anywhere on the image in the sky, and it will put a little, again, the contrast of this projector doesn't really show it, but there's a little circular reticle here that has a crosshairs and says, I'm looking at M20. And so if I want to research M20, I can basically click on, I want to know information, look on ADS. This is the astrophysics data system that Tony mentioned in his keynote. And if you do that, you get you send a query out, and this is a list of astronomical papers from the ADS system. And from that, I can click on to get the PDF of the paper, and I can directly read it, sort it, do all the sort of things that this is a step that in my community everybody does all the time. If I want to know what's going on, the first thing I do is do a query in ADS. And so instead of doing that query with text, I can do it visually through Worldwide Telescope, which is a really, really, really effective way to do that. Another thing you can do is you can add images. So FITS is a standard image format for astronomy across almost all domains. So it's one of the nice things about astronomy is we have one kind of standard format. And if I get now cubes aren't currently supported, but single images are. But we should think about the cube scenario. But I can just drop this in. It knows the coordinates in the sky. So as you saw from my other talk, I look at the galactic center. And again, this is kind of that mini spiral I was showing you in the other talk. But this is a FITS file that I just plopped in, and it gives me a little. I can click on that, and it pulls up a little color mapping tool to allow me to map color and contrast and change the ratios. And then I can crossfade this foreground image and see how it lies against whatever background image I put up there. So if I can crossfade between a molecular map from ALMA and a high resolution radio map from the VLA, and that can be a very powerful way to intercompare multiple data sets. There's another way to do this, called a VO table, or a virtual observatory table. And that's a way to exchange, where especially catalog information. If a person has, a classic example is catalog the stars in the Pleiades star cluster. So there's a catalog of positions and colors and brightnesses. I can make a query, and there's the virtual observatory program has a query for that, and then I could essentially, again, you can't read this because of the resolution of the screen, but this is a list of data sources that match some lists, and then I click on here, and it would plot them as points onto the image, and then I can investigate the points themselves. So if I want to know what that star is, I can hover over that point and it would give me that text back. So there's a lot of powerful ways to enable Worldwide Telescope to really enable types of scientific research. So the kind of scenario that I like to tell about how I use Worldwide Telescope, and I think it's one that's not so crazy for other astronomers to use, is to I first want to know where to point the telescope. So I want to make sure that I'm pointing at the right place. So it's very easy to kind of plop down telescope pointings on the sky, and then so I use it for observational planning. If I want to share that with a colleague, I should also mention that one of the design principles about Worldwide Telescope from its earliest inception was a combination of what's called tours, or kind of guided experiences, which once you play them, if you weren't to interact with them, would look like a video. It's like pushing play on something. I can stop that at any point and interact with it. So it's a combination of guided narrative narration, where you're walking somebody through some path, versus free exploration, where they can go wherever they want in the universe. And so that ability to go back and forth is really powerful. So if I want to share a tour with a colleague, if I let's say I want to put a bunch of pointing patterns down and say, what's this look like? I send them it's a very tiny XML file. And if they have Worldwide Telescope, and actually it works either in web or desktop versions, it'll just show up. And so I can share that. They can adjust it, send it back to me. It's a very easy interchange format. And so the idea is I might do observational planning with that. Then I get I write my proposal. It's very well written. It gets accepted by the reviewers, and I'm allocated time. I get the telescope runs, gives me a FITS image. I plop that in Worldwide Telescope. I can see it immediately, right? And then I want to thank you. I want to make an image, a movie, which I actually intended to do for my talk, but had some problems with my computer last night. But I want to make an image of kind of zooming into this FITS image from a great distance. Just as most scientists do this, is kind of laying the stage for the talk that they're given. So I used it in my previous talk just with a series of images, but it's very powerful to do as a little movie, and Worldwide Telescope can do that very easily. And so I can make a video for a professional talk. And then let's say I want to make a highly produced video for a public talk. I can do that as well. I can add narration, I can add music, and I can publish that, and anybody else can use it. So that idea of being in one tool is very powerful. As Juan mentioned, I think astronomers and as a proxy for people are lazy at some level, and we want easy to use tools and things like this where I learn it once and I can use it for all these purposes, whether it's outreach, my own research, preparing for research, or all different things. So now where's Worldwide Telescope going? The team is working on several things kind of almost all the time, but these are kind of what I think are the new exciting places we're going. One is always keeping up with new data sets. So there is this ability to bring your own data in, and that's very powerful as a researcher, but for the general public, they're not going to really have a great way to acquire data. They're more interested in knowing what's new. Most of the time when you see Worldwide Telescope, if you don't know anything about it, one of the first questions people ask is this live? Is this a live feed from someplace? Because it's so interactive, it has that feeling like, oh, I'm getting a feed from a live camera, even though there aren't live cameras looking down at the Earth all the time making images. I mean, there are, but they're not fed to us in real time. But the idea is, once somebody goes through there's a lot of work to take a bunch of individual images and make a global map or a mosaic image. Once you do that, Worldwide Telescope can very easily ingest that. The other idea is to visualize data sets from fast new telescopes. So these are things like ALMA, but we're actually working with a team from a telescope called LSST, and that is a telescope that's acquiring data at several times the rate, or many times the rate of even ALMA when it gets up and running. So, but the idea of bringing those data in is very important. Another thing is when observatories publish images, even as thumbnail images, we're working with NRAO and some other observatories. Instead of just having an image with some metadata around it, that image could be a Worldwide Telescope image easily. It would look like, and it could be interactive, and I could pull back and crossfade and do all the things that I want to do. That's a very powerful thing to do, and very easy to do. This idea of press releases, I think, is another very powerful thing. Most press releases have a big wide field context image. They have a square, like a box over something. They have a pull out of a zoom in of that box. And that can, instead of having really kind of cluttered graphic design, that could be one interactive image where the tour plays and text shows up and the thing zooms and it looks like a picture, but it actually is interactive. One of the things that we're really excited about is web-based authoring and sharing. So the idea is in the web, you could actually create a tour, share it with your friends, and you never really have anything locally. It's all stored in the cloud. So it's very much like YouTube or some other sharing of assets, but done completely in the cloud. And then it's a little bit of plug of something we're going to show at Demo Fest tomorrow is Worldwide Telescope with virtual reality and Oculus Rift is the head-mounted display we have. But one thing it doesn't do right now is have collaborative experiences. So when you're in this virtual environment, the next step is to put multiple people in the virtual environment. So I'm running Worldwide Telescope in my computer, you're in the United States, and you're in Chile, and we can both be in the same environment. A Connect is looking at both of us, and I can wave to you, or I can point to something with you with natural interfaces, and it's really, I think that's going to revolutionize how people collaborate, because they can actually embed themselves in this idea of a data set that Juan was talking about, the 3D model. You could take it and rotate it around and have two people look at it simultaneously in 3D, and one person can just look at it, look underneath it, point, say, what's that little blob right there, and the other people in the scene would also see it and be able to comment in real time. So that is a really exciting kind of direction this could be going. So these are just kind of an overview of Worldwide Telescope and some of its applications. It's primarily a astronomy data set now, but a lot of work has been done to abstract this to a generic data visualization system. So it's not, even though I'm an astronomer, I always want to keep the astronomy data. We can put in all sorts of data. We've looked at neurons. We've looked at various things that are way outside the astronomy realm, and think that it's something that really can be useful, especially for people who have existing analysis systems but want to have that visualization component without having to develop something from scratch. So anyway, I have take some questions. Thanks.
Let me ask you a question on my own.
Okay.
How does this compare to the so-called virtual observatories? The United States has one, for example, AUI and Aura running this.
Right.
What is the difference?
Who
who is the public? How is this oriented to?
Yeah, we are working, we go to MVO meetings, and we're very aware and plugged into those communities. And we do, when there are standard interfaces are what virtual observatory is actually creating. The idea is that different observatories create their data, they make it available through a virtual observatory interface, people can exchange it back and forth. And Worldwide Telescope is kind of committed to where it makes sense to do so, to be plugged into that, so we can take data into it. And it does satisfy that visualization component of it. It'll never really be an analysis sort of system. It probably won't have you won't be able to run you could maybe build your own analysis software using this as a visualization engine, and that's a nice complement. There is an interface called SAMP. It's an interface to exchange data from an analysis to a visualization, or analysis to analysis, or analysis to visualization package, basically to interchange data from application to application. And that's a very powerful way to do that as well. So you could have a desktop or a web service, like a VO service running, and then move it over via SAMP into Worldwide Telescope.
Thank you. Okay. See, questions? Nobody? How many people are working on this project altogether?
Oh, it's a small team. It's primarily Jonathan Fay is the principal developer. I'm a consultant kind of on the science side of things and the content. We have a web developer at some level of effort who's working in HTML5 implementation, which is very powerful. We have a little bit of a graphic designer, and so it's a very tiny team. So it's amazing that this much work has been done with essentially one full-time programmer for 5 years, or since launch.
Congratulations.
Yeah, well, thanks to Microsoft Research. It's a great investment. Yeah, he is not typical. Yeah, he's I've worked with a lot of great programmers on the astronomy side of things, and Jonathan is the best programmer I've ever worked with.
So this could be a research tool, provided that when you compare or you add up data from different telescopes, you have the proper calibration and you understand what system of in what units you are.
And that's what makes FITS a nice interchange format, because that has a header that
Okay.
has that information, it has a coordinate system, and we read that directly.
Okay, thank you.
Yeah.
Okay, we're out of time. Let me make a thank you very
Okay,
much.
thanks.